Hello students, in this section we will be concentrating on some very interesting numericals based on Gauss's theorem and certain expressions which we have derived using Gauss theorem, right? Let's first take the example of a cube. Question is a charge cube. This is a cube, a charge cube. Let us consider it to be small cube is placed at the corner of a cube, any corner. Suppose this is charge cube, it is placed at the corner of a cube. We need to find out the electric flux associated with this cube, right? So it's a complicated scenario. We need to make this much simpler using Gauss theorem. Directly we cannot use Gauss theorem over here because if you consider this to be Gaussian surface, then it is not enclosing charge. Charge is situated at the corner of the cube. So what logic says is, by virtue of symmetry, what we consider is, we'll consider 8 such small cubes which will bond together to form a big cube. Suppose this cube is of radius A. This is of radius A. So imagine a big cube of side 2A. This is a big cube of side 2A, and this charge is located over here. This is the charge, right? Try to understand the situation. So this is the cube which is given. At the corner of the charge cube is given. We need to find out the flux through this cube, which is shown with the help of dark lines. Dotted lines represent imaginary lines. So 8 such small cubes will make the big cube of side 2A. Isn't it? Now consider the case of the big cube. So this may be considered the big cube of side 2A. It may be considered to be a cubical Gaussian surface enclosing this charge Q. So directly apply Gauss theorem. The net flux associated with the big cube, it would be given by 1 by epsilon times the net charge enclosed. No doubt regarding this, right? This is the flux associated with the big cube. But our objective is to find out the flux associated with this single cube. And 8 such small cubes make that one big cube. Therefore, logically, the flux associated with one small cube, it would be equal to 1 by 8 times the flux associated with the big cube. So we get 1 by 8 q by epsilon. This is the form. Or rather, this is the result. Now, it is the case which is valid when the charge is placed in air or vacuum. Now, imagine a situation where, suppose it says that the cube is filled with some medium of dielectric constant K. In case of vacuum, this is the appropriate expression. But in case of medium having dielectric constant K or relative permeability epsilon r, the result will get changed. In this case, flux associated with this small cube would be given by q divided by 8. In place of epsilon naught, we need to write epsilon, which represents the absolute permittivity of the medium in which the charge is placed. Right? So, we are aware of the relationship between these two. We know that dielectric constant of a medium is defined as the ratio of the absolute permittivity of the medium to the absolute permittivity of free space. So, small q, the flux associated with it, it will be given by q divided by 8. In place of epsilon, you can write it as k epsilon. So, this will be the result of the above question in case the charge is considered to be placed in a medium of dielectric constant capital K. I hope you have understood it. Now proceeding with another such question related to cube, let us imagine again the charge to be placed at the corner, right? What will be the flux associated with each face of the cube? Earlier what we have done was, charge is situated in the corner, and this is the flux associated with the entire cube, the small cube. Now I am asked in the same question, flux associated with one face of the cube. Now concentrate on this diagram. These are the faces, first, second and third. This one, this is the third face. This charge, it is in contact with these three faces. This one is the first one, right? This is the first one, the top one. This is the first one, second one and third one. The charge is shared by three faces, right? So, if the flux associated with the small cube is 1 by 8 epsilon, and since the charge is being shared by three faces, therefore flux associated with a single face, it will be equal to 1 by 3 times the flux associated with the small cube, isn't it? So as a result, what you get is 1 by 3 times flux associated with the small cube is 8 epsilon. So the result would be Q by 24 epsilon. The charge is at the corner, so it will be shared by three faces, 1, 2 and the top one, right? Three faces. So this is in the case of a single cube. So as a result, the flux associated with the single face would be equal to 1 by 3rd, the flux associated with the entire cube. That is what we have done. So this is again a very, very important result. Other question related to cube. This is a cube, and let us imagine a charge cube to be situated at the center of the space or any face of the cube. So what would be the flux associated with the cube? Again, since the charge is placed on the surface, we can't apply Gauss theorem over here directly. For that we need to imagine some sort of Gaussian surface which must be enclosing this charge. And by symmetry, we will consider it to be a cuboid. Suppose this is a cuboid consisting of or made up of two cubes. This is an imaginary one. Now, with the combination of these two cubes, we are able to make this cuboid. Now, this is a cuboid. Gaussian surface in the form of a cuboid which is enclosing a net charge Q. The flux associated with the cuboid, which is made up of two cubes, would be equal to, as per Gauss theorem, Q by epsilon naught. The flux associated with a single cube, when the charge is placed at the center of any of its face, obviously would be half the flux associated with the cuboid, because it is made up of two cubes. So the answer would be, substitute the value, Q by 2 epsilon. So these are some important results which might be asked. There are some other questions as well. There are some other important questions as well. Like, we'll consider the case of a ring or a loop. Suppose a loop or a ring of radius r is given, and a charge q is uniformly distributed over its circumference. We are considering this case. Suppose it is a loop or a ring, say of radius r, and charge is uniformly distributed over its circumference like this. Charge q is distributed over its circumference, right? Listen to the question very, very carefully. Consider a spherical surface of the same radius whose center lies on the circumference of the given ring. I repeat, consider a spherical surface of the same radius as that of the ring lying at any point on the circumference of the ring. Suppose this is the center of the ring and this is the center of that particular spherical Gaussian surface of the same radius. So draw this surface. This is the spherical surface. I am representing it with the help of a dotted line. Now the question is, what is the flux associated with this spherical surface? So I'll repeat the question. Charge q is uniformly distributed over the circumference of a ring of radius r. A spherical surface, identical, that is of the same radius as that of the ring, has center at any point on the circumference of the ring. Find out the electric flux associated with this spherical surface. Right? Obviously, it will be treated as a Gaussian surface because it is enclosing this charge. This charge is lying outside, so it is immaterial. So this charge is being enclosed by the spherical Gaussian surface. Let it be Q dash. Obviously, it will be less than that of the net charge, but it is enclosing some sort of charge. So directly, if we apply Gauss theorem over here, the flux associated with the spherical surface would be simply given by 1 by epsilon times the net charge enclosed by the spherical Gaussian surface. So this will be the result. But in the question Q is given. So our main objective would be to convert Q dash in terms of Q. So that's the important step, right? So what we'll do is we'll make use of some mathematical concepts. Look, you can join these two. This is the radius, so this is the radius. This can be treated as R, right? This is also radius. This can be treated as R. Now, if you connect this from the center to the surface, same radius. If you connect this also, it will be also equal to R. Now consider this important concept. All the sides of this triangle are equal. So we are talking about equal triangle. These are the two equal triangles. All of side R. So each angle of an equal triangle is 60 degree. Let's consider these two angles. This is 60 degree. This is also 60 degree. So the entire angle, this angle, will be 120 degree. It will be 120 degree. This entire angle will be 120 degree. So we can easily determine the length of this arc, of this portion of the ring. It is subtending an angle of this length of the arc is subtending an angle of 120 degree. Total angle is 360 degree. So that will be the entire length. Entire length of the ring will subtend an angle of 360 degree at the center. So in case it is subtending an angle 120 degree, 1/3, its length will be also equal to 1/3. So if the total length of the ring is L, it subtends an angle of 360 degree. So 120 degree means 360 divided by 3. We are talking about 1/3 angle, right? So the length will also be equal to 1/3. You can make use of the formula for the length of the arc. It is theta by 360 into length, isn't it? Or 2 pi r. So by that also you can easily gauge the fact that if the total length, which is the circumference of the ring, is considered to be L, then it will be equal to L by 3. 1/3 portion of the ring is being enclosed by the spherical Gaussian surface. And as per the question, charge Q is uniformly distributed throughout the circumference of the ring. So if the length of the ring enclosed is L by 3, therefore the charge enclosed by the Gaussian spherical surface would be also 1/3 of the total charge. So Q dash, it must be equal to Q by 3. So as a result, the electric flux associated with the spherical Gaussian surface would be Q by 3 epsilon. So this is a very interesting question indeed. I hope you have understood the concept involved in this particular question, isn't it? There are some other very interesting questions as well. Suppose two plain sheets of charge of negligible thickness, each having surface charge density of plus sigma, are placed perpendicular to each other. Like this, they are placed perpendicular to each other. I'll represent with the help of a diagram. Suppose, let me try to represent it with the help of this diagram. Suppose this is one of the plane sheet having positive charge density, say plus sigma, and this is another one. This is another sheet, and both are placed perpendicular to each other. And remember, they are of negligible thickness. This is the first sheet. Suppose this is the second sheet. Both are of the same charge density, and they are placed perpendicular to each other. They are placed perpendicular to each other. They are placed perpendicular to each other like this. What is the electric field at any point over here? Any point. It can be over here, here, any point. Suppose these are the two perpendicular plane sheets, any point in this space. What would be the electric field at that point? Suppose this is point P. Now look, it's a very, very interesting case, right? In order to solve this question, we need to have some previous knowledge, right? First is electric field, as we are aware, due to a plane sheet of charge is independent of the distance of the observation point. And here the charge densities are equal. So electric field at point P, due to these two plane sheets having negligible thickness, are also equal, each being equal to E, say. And it will be equal to, what's the formula? It is sigma by 2 epsilon. I've told you these sheets are having negligible thickness, right? So this is the formula, right? Each electric field. Now, electric field is a vector quantity. So we need to solve it by using vector diagram. We need to make use of laws of vector addition. So this is a plane sheet. Consider the second one. It's a flat one, lying horizontally, right? Positive charge. So at a point over here, the electric field due to this plane sheet would be in the away direction. Electric field always emanates from the positive charge. So it would be like this. This is E2. This is the electric field due to this surface lying horizontally. What about the electric field which is lying vertically, like this, at the same point? It will be again in the outward direction. So it will be like this. This is E1. So what's the angle between these two? 90 degree. And both are of equal magnitude. So using the concept of laws of vector addition, whenever the two vectors are of equal magnitude, their resultant tends to bisect the angle between them. So this will be the resultant. This will be the resultant. It will make an angle of 45 degree. Now let's find its magnitude. Direction we have done. Let's find its magnitude. So the resultant electric field at point P would be given by square root of, you are aware, square root of a square plus b square plus twice ab cos theta. Here theta is 90. The angle between these two is 90. So cos 90 becomes 0. We will be left with square root of a square plus b square. And each is equal to e. So it will be e square plus e square. That is root 2e. Substitute this value of e over here. So we get root 2 sigma divided by 2 epsilon. This will be the magnitude and this is the direction. So this was again very, very interesting question, right? Let's discuss some other questions as well. I have told you earlier, if electric field is given, then the potential at a point can be easily calculated, and vice versa also. If the potential at a point is given, then the electric field can also be evaluated. Let's see. Let's do this question as well. Suppose the electric field varies with distance x as 10 by x square, where the electric field is in Newton per coulomb and distance considered to be measured in meters. We're dealing with SI system. So we need to find out the potential at x equals to 2 units, right? So the question is, the electric field varies with distance x as e equals to 10 by x square. We need to find out the value of potential at x equals to 2. How to proceed? We know that these two are related by electric field at a point is numerically equal to the negative of the potential gradient. This we are already aware, right? Over here, you can rearrange the terms like this. So potential would be given by negative of the line integral of the electric field. That is the statement which we obtained in the earlier section as well. Now substitute the value. Over here what you get is 10 by x square dx. 10 being constant, it can be taken outside. Integration of 1 by x square, that is equal to minus 1 by x. So we get 10 by x. So therefore, the potential at x equals to 2 would be equal to 10 by 2, which will be equal to 5 volt. So basically, if the electric field, its variation with distance is given, then the potential at a particular point can be easily sorted out, and vice versa also. So, I'll give you an assignment. You need to Try this particular question. Question is, the potential at a point varies with distance x and y, right? As v is equal to x square minus y square. The potential at a point varies with x and y coordinate as v equals to x square minus y square. You need to plot a graph showing the variation between electric field and distance x or y. You need to plot a graph showing the variation between electric field and distance. Right? This is as an assignment for you. I'll provide you the hint. What we need to do is, potential is given. So try to find out the expression relating electric field and x and y. And thereafter check whether they are linear dependent, whether it obey inverse square law. So accordingly you will get a straight line or you will get rectangular hyperbola. So this is the question which needs to be done by you. At least try to attempt it. Give it a sincere try, right? So formula again to be used is minus dv by dr. And try to solve it using vector form. R vector in terms of x, y, z, in terms of 3 dimension, it can be written as xi cap plus yj cap plus zk cap. Electric field is space. It may be written as exi cap plus eyj cap plus ezk cap. So try to make use of this. Only x and y coordinate are given, so you can avoid the z component. It's a 2D case basically. So make use of these concepts and try to plot graph between E and X using this particular formula, right? So students, try to revise all these numericals, practice hard. Numericals, they are important and rather they are integral part of physics. Once the theoretical concepts are clear, do practice as much numericals as you can. Chalo, happy learning.